All right. So we want to look at the non-uniform memory access. That's the NUMA technology, and snapshots. Right. So like I said, I don't want to take much of your time. So let's look at these concepts as quickly as possible. All right. So NUMA stands for non-uniform memory access. It's a technology that is used to improve data read and write speed. Okay. How it increases the data read and write speed is by making sure that each CPU core has memory access, has its own memory access directly connected to it. So it reduces the time that it takes for the CPU to be able to access memory for reading and writing. So you might have noticed that these days, most of the computers, if not all of them, have several cores in terms of CPUs, because having one CPU has reached a bottleneck. In other words, it has reduced the performance of computers. So computer designers or PC designers, they have ensured that each PC has more than one CPU core to improve speed. Right? So normally, the CPU and memory are connected through the north bridge. They are connected through the north bridge. And now what happens is, if we have one north bridge and we have one CPU, the speed through which data can move along the north bridge does not really get affected. But the moment we have several CPU cores accessing the same north bridge, it's going to reduce the speed because they are all going to scramble for one bridge, which is not expanding in size. Right? So you would see that as the number of CPUs increase, the memory is now also increasing. That's what they are now doing. They are increasing the memory in response to an increase in the number of CPU cores. So the response speed on the bridge becomes slower and slower because of increased number of cores sharing the same bridge. Therefore, designers have then evenly bound the memory to each CPU to avoid congestion caused by sharing the north bridge. So this is what happens in a setup where NUMA is not involved. We have our CPU here. This is the CPU. We have cores here. And then here we have memory. And this connection between the CPU and the memory, that's the north bridge we are referring to. So what happens is, for instance, let's suppose this north bridge can allow data, say maybe 300 megabits to pass through it at any given time. Right? If this CPU was the only one which was using this bridge to access memory here, let's suppose it wants to write some data in this memory. If this was the only CPU using this bridge, let's suppose this CPU was sending data to memory, data at say maybe 250, say maybe 250 megabits per second, for instance, right? 250 megabits per second. If it was the only one that was accessing this north bridge, given that the maximum speed of this north bridge is 300 megabits per second, it was not really going to affect the speed. Now, what would then happen is, let's suppose we now have this other CPU, which also wants to access this north bridge, and it wants to write data at the same speed again, 250 megabits per second, or 250 megabits. What is now going to happen here is, you see that these two CPUs, they want to access different memory locations here, but they want to use the same north bridge, which has a limit in terms of speed of 300. So what do you think is going to happen here? Do you think we are still going to have the same speed as it was before when we were just having one CPU here? Rachel, what do you think?
No, I don't think it will have the same speed because there will be two CPUs accessing one bridge, and the limit is not enough to accept both of them at the same time.
Yeah, that's true, because the maximum that can get through this bridge is 300. This one wants to send 250, this one wants to send 250. So it's either one of them is going to send all the 250 and the other one will send 50, or they are going to share somehow. Maybe the other one will send 150 and the other one will send 150 also. So what it would then mean is the time that was supposed to be taken by this CPU to process or to write and read data to memory is going to be reduced because of the limitation that is being imposed by this North bridge here. Right? So this is what used to happen before the NUMA technology was introduced. Right? Now let's see what happens after the introduction of the NUMA technology. So after the introduction of the NUMA technology, what happens is each CPU is associated with its own memory. So there is no need for the CPUs to be accessing the non-local memory using that North bridge. Right? So a CPU can access its own local memory faster compared to non-local memory. And as the local access speed is high, it is more efficient for a program to only use a CPU and its associated local memory. We have seen that if the memory is not local, we would need to go via a North bridge. But if the memory is local, there is no need for that North bridge, and that would increase the speed. So the idea is, it's unfortunate that I deleted that diagram. Okay, it's actually on the, I'll show it on the next slide. So this whole technology of having a CPU being given its own local memory, that's what we are referring to as the NUMA technology, or non-uniform memory access technology. So this is what happens now after NUMA is introduced. What is now happening is we are now saying for each CPU, it's now having its associated memory, which it can access directly. It's now having its associated memory, which it can access directly, instead of having to access the memory which was just here. So here we see again this CPU core, it has its own memory that is associated with it. Of course, there will be a connection that connects the CPUs, because the CPUs might need to interact with each other. So there will be an interconnect which connect the CPUs. But this is not for data reading or writing. So for reading and writing, each CPU will have its own memory, which is local to it, and there is no longer that thing of sharing the North bridge in this case. So this improves the speed. That's the whole concept of the NUMA technology. Any questions there? Okay, seems like there are no questions. So NUMA nodes, a NUMA node, if it is said to be a NUMA node, it means it is a combination of CPU and memory couples. We have CPU and memory as a coupled together. That becomes a NUMA node. And each node has a CPU, it is a bus and memory. Right. Now, by bus, you'd see that there is need for a connection. There are those wires which will connect the CPU to the memory. That's what we refer to as a bus, right? And then if there is need for cross-node access In that case, we would need to interconnect the CPUs. Cross-node access, that's what we are having on this slide here. This is a cross-node access. By node, we are referring to this part here. This is a node where we have the CPU and its associated memory. Here, this is another node. This is another NUMA node where we have the CPU along with its associated memory. So if there is need for inter-NUMA node communication, in that case, we would need an interconnect, which will connect the NUMA nodes. Again, this concept is usually asked, this concept of the NUMA technology. So in virtualization scenarios, NUMA enables VMs to use hardware resources on the same NUMA node, improving the VM response speed.